Hello, everyone. I am Arpan, one of the instructors for AI&D, and today I'm going to do a project walkthrough for the planning project. Just in case you missed it, hello, everyone. I'm Arpan, one of your instructors for AI&D, and today I'll do a project walkthrough for the planning project. All right, so if you're on this project right now, you have built an agent that plays Sudoku, right? You've built an agent that can play the game of isolation using heuristic-based search. Now, we're going to apply kind of the similar techniques of search, but in a slightly different way. That is, using logic to first define a problem space, and then using search to find solutions in that problem space. Cool. So let me start sharing my screen so you can all follow along. And I'll take all the questions later. Okay. Cool. Can everyone see my screen right now? Yes. Okay. Cool. So first things first, if you haven't already, please set up your environment. And what we recommend is for you to install Anaconda, which comes sort of with a lot of the numerical and scientific computing packages either installed, or it's pretty easy to get them installed there. The instructions for this are in the Setting Up with Anaconda lesson. So if you have everything installed properly, then let me change my screen share once. Right. If you have everything installed properly, then you source activate AI&D. Like that, and that should give you this sort of prefix in your prompt, which means you're in the AI&D environment. And here is basically a folder. This is just a blank folder I created. I cloned this repository, so you can get the clone link, whether you're using SSH or HTTPS, you can get the appropriate link, clone the project. That would give you fetch this directory, AI&D planning. Files, I'll basically open this in GitHub so it's easier to go through. All right, so once you're ready to start working on the project, definitely read through the instructions. I know they can be a lot sometimes, but there are finer points here and there that you probably don't want to miss. So as you can see, there are three main portions for this project. Let me make sure everyone can see my screen. Looks like I see myself. All right. Cool. So three parts for the project. First one, where you define the planning problems, again, using logic that you've been learning. And then in the second part, you implement the actual search portions. So you search for solutions, which are basically plans. And then the third part is writing it all up as a report. Cool. So the planning problems here are kind of based on the AI, A Modern Approach textbook. So it does help to read the appropriate sections. We have included a link to a PDF which contains those sections, but if you have access to a book, you can read a little bit more around that section to get a better idea as well. So the two sections that we want you to focus on are the planning problem and planning with state space search. Okay, now problems are, these planning problems are typically defined using logical notation, but in a fairly specific planning domain language. And if you are not familiar with this, you should be able to read up in the textbook section. But let me give you a quick idea of what this format means. Here we are defining an action. Okay, the action is called load, and it has these sort of three parameters you can think of. In order for that action to happen, you need to meet these preconditions. What are the preconditions? That at C comma A, which means C should be at A. In our air cargo domain, this basically means cargo C is at airport A. Similarly, and at P comma A, plane P, airplane P should be at A. C should be a cargo object, P should be a plane object, A should be an airport object. Okay, and what is the effect? Well, the cargo C is no longer at the airport, it is inside the plane. So that's what this is saying, not at C comma A and in C comma P. All right. So you can define actions like this, so that creates sort of the world of possibilities that can happen. And then you define an instance of the problem by specifying particular cargoes, airplanes, and airports, and where all these things are using logic. Cool. So you're given these three problem definitions. The first thing you have to do is implement the getActions method, and you can basically break down that getActions method in terms of load and unload actions. So let me open that code up, and in the meantime, let me check if everything is going okay. Cool. If there are any problems, let me know in this YouTube chat. I'll keep referring to it from time to time. All right. So if we look at the code repository, I just opened up my air cargo problems, and if you scroll down to the getActions method, this is what you first have to implement. And basically what you're looking for is given a problem definition. So you would have, this init function would have already been called. So you would have access to all the cargoes, all the planes, and all the airports. Now, basically, you need to generate a list of all the actions. And this is the function you have to implement. So remember the definitions here, right? So now you can see that there are variables in here, right? C, P, and A. For a particular problem definition, you have all possible instances of cargo, airport, and plane defined. So you basically have to define all possible actions in this getActions function. Okay, cool. And you can, internally we've broken this down into load actions, unload actions, and fly actions. And we've given you an example of how you would implement or how you would define these fly actions. So as you can see, the format is kind of like looping through all the possible objects that action sort of includes. So if you look at fly actions, you see there's a plane P, and there are two locations from and to airports, right? And this is what these loops are doing. You're looping over all possible airports that can go in the from portion or from slot in some sense, and all possible airports that can go in to portion. Make sure they're not the same. Then for all possible planes, you're basically generating the preconditions and the effects and putting them together into a fly action, appending that to a list of actions and returning that. So if you just follow this same sort of methodology and define the load and unload functions, that's pretty much it. You should be able to get done with this first part. All right, so once you've implemented get actions, go to actions, which is basically, now before this, get actions was all possible actions, but actions are the actions that can be taken in this current state, and state is given as a string. The string is basically a representation of which fluents are true in this state, right? And it's basically FT, 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 T for true, F for false. Based on which fluents are true and false, you need to return all the possible actions in the state, right? And this is what will get used in your planning search. So in planning search, just a quick reminder, at any point of time, you're in a particular state where certain fluents are true, which means certain actions are applicable, and you'll apply one of those actions to generate more fluents, and then those will basically create further states, and you then go through each of those states and so on until you get to a solution. Cool. Similarly, you have to implement the result method as well. Okay. So this is sort of I like the way this project sort of takes one step at a time and walks you through the whole planning process. So first you found out what all the possible actions can be in this particular cargo problem, air cargo problem. Then you computed what the current possible set of actions are for a given state. And then what is the resulting state once you apply that action in that current state? That's what you have to compute in the result function. Okay. And then, so these are the three functions or the three methods that you have to implement in the air cargo problem class, right? And then if you look at this function here, air cargo P1, this is basically given as an example of how you would define a particular problem, an instance of a problem. So let's go back and look at the definition in its logical form. You see, we're saying that there are two cargoes, right? C1 and C2. C1 is at SFO, C2 is at JFK. There are two planes, P1 is at SFO and P2 is at JFK. So let me see if we followed the same order here. Yeah, so at C1 SFO, at C2 JFK, at P1 SFO, at P2 JFK, right? That's all that has been given in terms of where things are. And then there are some additional logical statements or terms that basically say that C1 is a cargo, C2 is a cargo, P1 is a plane, P2 is a plane, JFK and SFO are airports, right? But to have a complete definition of the problem domain, you also need to specify all the negative fluents. And those are basically that, okay, if C2 is at JFK, then C2 is not an SFO, blah, blah, blah. So all of those are mentioned. Then you basically say that the initial state is all of these positive and negative fluents. And you define the goal as, what is our goal? To move C1 to JFK and C2 to SFO. That's what you express here. So this is how you would basically create an instance of an air cargo problem. And what you're being asked to do in these two to-dos, air cargo P2 and P3, is implement these two problems, problem 2 and problem 3, just like this P1 in these functions. All right, should be straightforward if you look at this as a reference. Note that some of these have, I think both of them have 3 cargos. Problem 3 has 2 planes. All right, so once you're done with this part, you've basically defined the air cargo problem class and then have had practice defining a couple of air cargo problems. All right, quick check. All right, nothing yet. Go back. Cool. Now, once you've defined the problems, now you have to start thinking about how do you search in this space, right? So there's this, I like this neat diagram here. If you think of the initial state of the problem as a list of propositions that are true or false, then you can have certain actions that are applicable in this state, and you try applying them, and you compute the result of applying that action to that state. And then you keep going forward. So you can see how this is like a search tree that is being formed. Ultimately, along one of these paths, you will reach the goal state where the things that you care about are true, right, or have been met, and the others, you know, whether they're true or not, it's, you don't care about that. So that's what basically the run search function does. And there are different search methods that that it can use based on how you specify it. So what we're asking you to do in this next section, you don't have to implement the search functions yourself. If you've had some experience with defining breadth first search and depth first search, this should be pretty straightforward. It's just that mapping this to the logical domain introduces some additional complexities, and we didn't want you to go through that unnecessary hardship. What is more important here is for you to run these different searches and see what the results are, how many node expansions are happening, etc. So, but for this, you obviously have to have the problems defined. So follow the instructions here to run these different searches. These are all uninformed search, right? So you're blindly searching through this space, basically applying all sorts of possible actions. Now, in the second part, you're going to use heuristic-based search. So the same searches that you were doing before, but now you're going to implement certain heuristics. And for this, again, you can go back to the book chapter and read it. Basically, we'll be using the structure called the planning graph in order to implement this. The first heuristic you want to implement is ignore preconditions. Let me go back to the code. So what is the ignore preconditions metric heuristic? Remember that in a planning problem or in any of these logical problems, you have to meet a set of preconditions in order to apply an action, right? But here we're relaxing that constraint by saying that, okay, let's assume we don't have to meet the preconditions. We can just apply the action. Then how many sort of steps will it take in order for me to go ahead and accomplish this, right? And we use that as a heuristic, right? It's easier to compute because you're not having to evaluate, okay, are these preconditions always met or not? It gives you sort of a bound on how many steps you would need to reach the goal state. If you use that as a heuristic, then you know which states are more promising, which might lead to a solution, right? And so you use that as a heuristic. more instructions in the textbook chapter. Try implementing this. This should be one of the easier ones to implement, honestly, because you're basically ignoring, the check for which actions are possible. You're just applying, all, all the actions that are needed in order to achieve a goal state. Cool. And then, so for this first one, we're actually not using a planning graph. But these other heuristics that you can implement will all use the planning graph, and they're in my planning graph. So let me go down to the heuristic that we want you to implement is basically H level sum. But in order to implement that heuristic, it needs these functions to be properly defined. So you have to define add action level, add level, and if all of this does not make sense, definitely read up about the planning graph. The planning graph is a neat structure that takes a particular planning problem and then generates sort of an optimized data structure where certain conditions and actions are linked in a way that you can then quickly reference through it in order to find a solution. In this case, we're not going to use the planning graph to directly find a solution. What we're going to do is use the planning graph to compute a heuristic and then apply that to our search function. So the heuristic we're interested in is level sum. And as mentioned here, it's the sum of the level costs of all the individual goals. Cool. And there's more, like there's a to-do here, which basically spells it out for you. For each goal in the problem, determine the level cost and then add them together. Cool. So, and just to give you a quick reference, level means at what level in the planning graph is that particular goal state being met. So you want to add all those different level numbers for the different goal states that are required, and that's your total level sum. All right, so once you've implemented these planning graph methods and the heuristic H level sum, now we are asking you to basically run a star search on these three problems using this heuristic, and then report basically these metrics, which are number of nodes that were required, or node expansions that happened, number of goal tests that were carried out, the time elapsed, and you can take a look at the solution that is coming out, and you can compare them. One of them should be the optimal solution. Ideally, all of them should find the optimal solution, but we want you to comment on whether your solution was optimal or not. Cool. All right, so once you've implemented that, and this is just a small excerpt about the planning graph, I mentioned before that you can extract a plan directly from the planning graph, and that is called the graph plan algorithm. For the purpose of this project, we're not asking you to implement graph plan, but if you want, you can definitely extend this to implement graph plan. It's a little involved in figuring out exactly what all you need to do, but it's a really neat algorithm in the end, because you don't have to go through the hassle of computing heuristics on every search call. All right, so once you're done with that, there are instructions for what you need to include in your report. Basically, we want you to both implement the problem class, some specific instances of the problem, heuristics and then run these search algorithms using the heuristics and then report what you found. All right. Now for submission, and by now you should have used the project assistant. If you're in the correct directory, you should be able to run Udacity submit, and that will submit your files to the project assistant online. It will run some tests and return results back. Right now I haven't implemented any of this here, so pretty much all of my checks should fail except for air cargo P1, which we have implemented as an example. So you'll see dots there, but the others either errored out or failed. Errors mean basically something went wrong, so most of the functions which are not implemented will probably error out because they're not returning anything useful. And then the ones that fail are probably returning something in an appropriate form, but it's incorrect. So once you start implementing these different functions, keep running Project Assistant from time to time and make sure that they're slowly getting checked off. And by the end, you should have all of these correct, and then you can submit it for review. All right, that's all I had for the main walkthrough. Just remember that in your final submission, let me run this again. Right, so you can see that the Project Assistant lists the two files that are being submitted. So you need to submit these two and then your written analysis. Cool. All right, let me get back and make sure I didn't miss anything. Right. The other portion that I forgot to mention is your research review, which is explained here. We basically want you to go ahead and read the literature on planning and search, and then write a one-page report on 3 important developments that you've found. All right, let me turn off the screen share and then I can take questions. All right. So let me scroll up and see if anyone had questions while I was speaking. Doesn't look like it. I know it's early in the morning for a lot of people. So Ellery is asking, can I get a recording of this? Yes, these Hangouts on Air are recorded automatically. Darshit was asking, what time are we starting? I guess when you asked, we had already started. Cool. Julio, you have a question? So Julio's asking, the classes, action, and so on are not really well documented, and we have to use them. in order to implement the methods in the graph, especially. Question still coming. But yeah, in general, I know that the AIMA code library is not as well documented as we'd like it to be. But the good thing is that it is open source. So you can go ahead and look up the relevant code. But more importantly, I think what will help you out more is to look at an example. So we have included, let me share my screen back with you all. Okay, so there is a more specific question. Am I correct that the extract solution for graph plan is not given? Oh, someone else. Let me continue with Julio's question first. For example, I wasn't able to figure out how to use action.check precon. So let me see what I'm looking at. Okay. So if you're going to run search, actually, so the portion of AIMA code that is relevant to this is included here. And if you open the planning.py file, then you can see the entire definition for the action class, right? And you can see what the check precon function does. It says checks if the precondition is satisfied in the current state. And the state here is passed in as, let me make sure I'm doing this right. Yeah, is passed in as a knowledge base, KB, right? So you're basically going through all of the preconditions, right? And then now remember that an action is basically an action schema, right? So you instantiate by substituting any variables that are there in your action with the arguments that are being passed in, and then you see whether it is present in the knowledge base or not. And you do this for all possible preconditions. And if any of them doesn't match, then it returns false. Similarly, it checks for negative preconditions as well. And here, just the check is different. If all of these checks pass through, then it returns true, right? So I think one of the subtleties here is that you have to pass in the current state as a knowledge base. And if you want to look at how that is done, let me see if there is an example of a knowledge base here. So you can create, so I'm looking at example have cake, and you can see how you can create a knowledge base. This is a propositional knowledge base. And you basically take a given state and a state map. You decode that state from the FT string to different fluents. You create a sentence of basically ANDed fluents from that, and you pass that on to the KB. So this is how you can basically initialize a knowledge base from a given state. And once you do that, then you can use this KB to check preconditions or to carry out other verifications. All right, let me go back to looking at questions. Oh, so who you're saying he didn't know what the args argument was supposed to be. Correct. So let me go back to check precon. You can see the way args is used is to substitute this actions variables. So if there are any variables, now if your action is completely propositional, then you don't need to pass in anything, or I think you can basically pass in an empty list in args, and that should be okay. But if your action actually has variables in it, then you can replace those variables by passing in args. Right, let me see. QCartung has a question. Am I correct that the extract solution for GraphPlan is not given since we are not using it? I'm not sure what extract solution for. Oh, so yeah. So we're not asking you to implement or use GraphPlan. Share, right? We're only asking you to use the planning graph to compute the different heuristics. Is that clear, or were you asking something different? Okay, I'll take that as a yes. And if we don't have too many questions right now, we can wrap this up early. But definitely let us know if you have any questions in the Slack channel. I think the Slack channel is P-logic and planning, or P-logic planning in the ND, no, in the AI-ND Slack. And okay, cool. And we're definitely expecting that it'll take a significant amount of time for you to go through this project. So don't delay working on it. Definitely get started as soon as you can. The search functions do take a while to run. We've already taken steps to make sure it is more optimized, but we know that it can be optimized even further. We're working on that. But you don't get disheartened if your search takes a long time. It is supposed to. So, and we want you to basically reflect on that. And thanks, Lisbeth, for pointing out the Slack channel. Let me see my notes and make sure I'm not missing anything. All right. I think that's about it. I'll hold my peace and we can resume back on Slack, either in the channel mentioned there, P-logic and planning, or you can also see me during office hours. And good luck with the project.